Hi guys, this is part 4 of your Unit 9 gas loss practice problems, and we're going to talk about the ideal gas law in this one, along with Dalton's law of partial pressure. So with the ideal gas law, it's going to allow us to examine the relationship between pressure, volume, temperature, and number of moles of a sample gas. Now your R constant kind of determines what all of the values are for your PV, N, and T are, and there's lots of different R constants, but I prefer to use this one right here. So because I'm using this value for R, my pressure is going to have to be in atmospheres, my volume will have to be in liters, N will have to be number of moles, and temperature will have to be in Kelvin. So let's go ahead and do the first one. It says, what volume occupied by 3.760 grams of oxygen gas at a pressure of 88.4 kilopascals and a temperature of 19 degrees Celsius? Assume oxygen is ideal. So I'm solving for volume. I'm first going to have to convert my number of grams of oxygen gas to moles of oxygen gas. So N, so 3.760 grams of O2, we're going to convert to moles of O2. My pressure, P, I have to convert from kilopascals to atmospheres. And then my temperature, T, I'm going to have to convert from Celsius to Kelvin. So in order to do that, the first thing I'm going to do is divide this by its molar mass. So on my periodic table, the mass for oxygen is 15.999 because it's O2. We're going to multiply that by 2 to get that number. So let's do 3.76 divided by 31.998. That's going to give me approximately 0.1175 mole. And I like to round to the very end, so I'm going to give several decimal places for each one. All right, for kilopascals, I'm going to multiply by my conversion factor. 1 atmosphere is to 101.325 kPa. So 88.4 times 1 divided by 101.325. That gives me 0.8724 atmosphere. And then with my temperature, I'm just going to add 273 to get that into Kelvin. So 19 plus 273 gives me 292 K. So I'm solving for volume. My formula again is PV equals nRT. So I'm solving for volume. So I'm just going to divide this by P. So V equals N times R times E over P. So let's go ahead and plug that in. So my N value is 0.1175 mole times R, and I said I'm going to use this gas constant R, so 0.821 liters times atmospheres over moles times Kelvin, times my temperature in Kelvin, which is 292 K. And I'm going to divide that by my pressure in atmospheres, which is 0.8724 atmospheres. And then we will figure out significant figures after we do this. Let's go ahead and do this here. So we're going to do 0.1175 times 0.0821 times 292 divided by 0.8724. All right, so I get 3.22 something, 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 something. And I need, that's 4 significant figures, 3 significant figures, 2 significant figures. So let's do 2 significant figures. So we're going to do 3.2, and then we're doing volume, so that'll be in liters. Another way to check this is if you use your R value, I can go, okay, atmospheres cancels, moles cancels, Kelvin cancels. I'm left with liters. So that's the first one. We're going to do each example where we solve for each different variable. So the next one, it says 6.2 liters of an ideal gas is contained at 3 atmospheres and 37 degrees Celsius. How many moles of gas are present? So awesome. On this one, all we have to do is do the conversion for temperature. So T equals 37 degrees Celsius plus 273. Which is going to give me 310 Kelvin. Let me focus that for you. Oh, it does not want to focus. Hold on, guys. There we go. All right. So we're solving for N. So again, PV equals nRT. Solving for N, so I divide by RT, divide by RT. So N equals PV over RT. So pressure was 3 atmospheres times my volume of 6.2 liters, divided by the R value again, which was 0.0821 liters times atmospheres per mole times Kelvin times my temperature in Kelvin, which is 310 K. All right. So if you notice, I did put parentheses here on top and bottom, and I want to make sure I do the same thing in my calculator so I don't get a funky answer. So let's do that real quick. So parenthesis 3 times 6.2, close parenthesis, divided by parenthesis 0.0821 times 310, close parenthesis. I'm going to get this big old long number. I've got 2 significant figures, 2 significant figures, 2 significant figures. Oh, so let's go for 2. And we're going to get 0.73 moles. That's N. And again, you can just cross out to make sure your variables cancel. We're left with moles. Okay, let's do number 3. It says, I have 1.9 moles of a gas at a pressure of 805 millimeters of mercury in a container with a volume of 500 milliliters. What is the temperature of the gas? So we're going to do a couple conversions. For pressure, it's in millimeters of mercury. So we're going to have to convert that to ATM. And volume is in milliliters. We're going to have to convert that to liters. So this one, super easy. Divide by 1,000 to get that to liters. This one, I'm going to multiply by my conversion factor. 1 atmosphere is equal to 760 millimeters of mercury. .805 times 1 divided by 760. Okay. 0.0590. Atmospheres. Again, I'm doing lots of decimal places because I will round at the very end. All right, so now we are solving for T. So PV equals nRT divided by nR divided by nR, and I get T. So T equals PV over nR. And again, parentheses, so 1.0592 atmospheres times my temperature. Oh, wait, no. Times my volume. We're solving for temperature. Times my volume, 0.5 liters, divided by number of moles, 1.9 moles, times that ideal gas constant, which is 0.0821 liters times atmospheres per mole times Kelvin. Right. So parenthesis 1.0592 times 0.5, close parenthesis, divided by 1.9 times 0.0821, close parenthesis. All right, and I'm going to get this big old long number, and we're looking for significant figures. We've got 2, we've got 3, we've got 1. So we'll do 3 Kelvin. All right, now let's go ahead and do our last ideal gas one. So it says, if I have 162 grams of chlorine gas held at a temperature of 97 degrees Celsius in a container with a volume of 465 milliliters, what is the pressure? So let's do some conversions. So for N, I have 162 grams of chlorine. T, 97 degrees Celsius. V, 465 milliliters. Let's divide that by 1,000 to get my liters. Plus 273. We'll have to divide that one by its molar mass. So let's do 97 plus 273, 370. All right. Chlorine on my periodic table has a molar mass of 35.6 0.45, so it's Cl2, so 35.45 times 2, 70.9 grams of chlorine. That would be my molar mass. 162 divided by my molar mass gives me 2.285 moles. So now let's go ahead and solve. And we are solving for pressure. So again, PV equals nRT. So P equals N times R times T divided by V. So 2.285 moles times that gas constant, 0.0821 liters times atmospheres per mole Kelvin. Oh, just want to focus right now. Okay, times temperature, which was 370 Kelvin, divided by that volume of 0.465 liters. All right. So 2.285 times 0.0821 times 370 divided by 0.465 gives me this big old long number. I'm looking for two significant figures, so we'll round that to 150 atmospheres. Okay, so let's talk about Dalton's law of partial pressure now. So Dalton's law of partial pressure tells us that the total pressure of a mixture of gas is the sum of the individual or partial pressures. Each gas is assumed to be an ideal gas. So when we do this, the big thing is that we have to make sure all of our pressure units are in the same, or all our pressures are in the same units. So let's go ahead and do two of these. The first one, I'm told I have 35 atm of oxygen, 5 atm of nitrogen, and 25 atm of helium. And we want to know the total pressure. So that just means I'm going to add 35 atmosphere plus 5 atmosphere plus 25 atmosphere. And what is that? 65? 35 plus 5 plus 25? Yep. So that's going to give me a total pressure of 65 atmosphere. On this one down here, we got a little bit something different. It says we have a mixture of carbon dioxide and oxygen. The total pressure is 1.2 atm. The partial pressure of oxygen is 524 millimeters of mercury. What is the partial pressure of carbon dioxide in kilopascals? So we know that our total pressure is equal to oxygen plus carbon dioxide. So we're going to solve for the carbon dioxide. And to do that, we're going to have to subtract your total minus your oxygen to get carbon dioxide. But first, we've got to convert everything into kilopascals to do this. So P total is 1.20 atm, and P pressure of oxygen is 524 millimeters of mercury. So let's go ahead and convert these to kilopascals, and then we'll do the problem. So I'm going to multiply that by that conversion factor. So 101.325 kilopascals over 1 atmosphere. We're going to multiply this one by the conversion factor, 760 millimeters of mercury on bottom, 101.325 kilopascals on top. Okay, so on the top one, I have 1.2 times 101.325 gives me, what's this say? Sorry. 121.59 kPa. All right, this other one, I've got 524 times 101.325 divided by 760. So I'm going to get about 69.994 kPa. All right, so then I'm doing total minus oxygen is going to give me carbon dioxide. So total, which is the top one, minus this one, give me carbon dioxide. Let's do 121.59 minus 69.994. All right, the rules for significant figures with addition subtraction is the least number of decimal places. So we're going to have no decimal places. So we're going to round this to 52 kilopascals. All right, there we go. I will talk to you guys later.